All right, why don't we get started today? Um, Today we're going to start chapter 8. And last year this was chapter 9. I moved it to chapter 8. 2 years ago it was chapter 11 or 12. And I moved it down. And then 4 years ago, we didn't even talk about this stuff. So this is I think a really cool topic. This is really getting at the heart of what you think of as AI today. Um, the large language models that we use today. And so this week we're going to talk about transformers. Transformers are the architecture that is currently underneath all the large language models. Um, Chat GPT, the T in GPT is transformer, generative pre-trained transformer. So what it is just a network that again has been pre-trained to generate text. Just a transformer for that. So we're going to try to look under the hood and understand how these work. Now you might ask, why do we need to look at under the hood to see how these work? A couple reasons. Um, it kind of removes the magic of them, where people and kind of lets you see what are these capable of and why do they work so well? What are they good at and what aren't they? Just how do they actually work? Sometimes that's useful to uh, not have some magic black box there, but really be able to kind of know what's underneath it. The other thing is that it'll help you evaluate going forward other technologies. Currently, transformers have basically taken over the world in the last 5 years here. Everything is kind of running on transformers there, but there are competing architectures out there, two or three that are quite important, and you're going to make a run for it. And so we don't know if transformers will be what will be the next evolution. I would I can guarantee that transformers aren't the end all of AI. They are just the next step here. So understanding how they work and the different parts of them will kind of help you understand what are the future steps likely to be and understand those steps when they happen. So this week we have a couple things. So explore 8. You can look at some different options here. Stanford did a nice high level review of GPT-3 and beyond at one point. They have a webinar talking about that, kind of walking through it at a high level. Again, so not down at the technical, like an MIT sometimes gets, but at a higher level there. Again, this is getting at newer stuff, so I don't have great courses on it sometimes. So Hugging Face has a course and some materials on transformers, but places like Google or Microsoft that I sometimes turn to don't have. Again, they're just so busy developing tools for this, they haven't done much in the way of training materials. So I do have some YouTube videos, and I've grouped a couple of them together that you can choose to watch. So I find some of those useful. Okay, so I'm going to jump into this resource and try to explain what transformers are to you here. First, let's talk about what transformers are built upon. So again, for the last couple of weeks, we were talking about recurrent neural networks, including long short-term memory. We talked a little bit about encoder-decoder networks, these networks that would take like a string of characters or an image and encode it into some internal representation and then decode it into another image or some text. So we see this both with text where we're maybe encoding it, taking English text, encoding it into an internal representation, and then decoding it into a different language. We briefly mentioned attention, which is a way module that we can add to these encoder decoder modules and stuff like that, that will help us kind of calculate what words are important related to other words in our sequence there. And so transformers are going to be built on this. And this one lists Bert at the top. This is an old video where Bert was kind of the top transformer model out there. But you could put, instead of Bert, you could just cross Bert out and put GPT right there, or Gemini, or any of the language models, all built right on transformers here. So, I actually this is I like this video. Let me just pop I'm not going to play this all. Just going to give you a hint at this video. Let me see if I can get it started without too many ads. So this is Google Cloud video. I forget her name. She's a Google Cloud technician, but she's walks through in a 10-minute or like 9 minutes an overview of how GPT works. And again, she's going to cover some of the same. She's going to talk about attention and show some of these graphs and talk about the different models here. So I really like her thing. But again, I'm going to try to do what she does. I think she might do it better than I do. So after you're done with me, you might just want to watch her there. Now I'm going to click on this article and kind of do an overview of what we're trying to do here. Unfortunately, this article's gotten very popular, and so it's been covered in ads, unfortunately. So we're going to look in just a sec at a 2017 paper by Google researchers called "Attention is All You Need" here. And again, we had these recursive neural network encoder decoder models. They were mainstream back in 2017 here. And they were recursive, and they had attention modules put in them. And Google said, you know what? You don't need the recursion. You can drop that, and attention is all you need with this. So that's where the title of this, attention models, you don't need the recursive models. And then this is the format for that transformer architecture. We'll be spending a lot of time on this particular diagram today as we go through this here. So again, encoder decoder architectures. So the idea is that we're sending inputs into a transformer and getting outputs. So here they're looking at a transformer for translating from English to French here. And again, the transformer part has an encoder and a decoder inside of it. So the idea is that we send in some inputs. We use the encoder to create some internal meaningful representation, feature space, sometimes we call this here, representation. And then from that, we have a decoder, which will take that feature space, that internal representation of that sentence or those words, and create the output. And again, the idea is that we could substitute different encoders and decoders in here to do different things. In here, and again, it's interesting. I really like to see the evolution, the combining of different ideas in different places. If you remember with convolutional neural networks, one thing we did is we did lots of layers so that we could detect more complicated features. So maybe we are just in an image, we were detecting just lines early on, and then shapes, and then faces here. And we're doing the same thing within this encoder. We have multiple encoders that stacked on top of each other. So the lowest level ones are detecting very primitive ideas, encoding very primitive concepts. And then as they go up and up, they encode more and more complicated concepts in this idea, in our sentence here. And again, same with the decoder. The decoder is mirroring this with taking the more complicated ones and going on to more basic ones that we can map right onto actual words. for this. So here's our overall view. We set our inputs, we feed it through a set of encoders, we generate a feature space that is sent to all of our decoders, and our decoders generate some outputs. So that's our general idea of this map now. So again, we're going to kind of group these in boxes again: inputs, the encoder, features, the decoder, the outputs, and then we're just going to set. So rather than just saying we have drawing all 6 of these encoders, we'll just put 6 times the encoder here, or NX is what they write. So they'll just say that this is duplicated multiple times like this, and same here. So that's our picture, is that these encoders and decoders are duplicated multiple times, stacked multiple layers deep for this. We're gonna want to talk about some things, embeddings or tokenizing and positional encoding. So the first thing is embeddings. We want to take words and convert those into numbers, and we use what is called tokens here. So every word will be changed into a sequence of numbers for this. And so every word will be a set of numbers that will be stored in our database for this. The numbers are kind of arbitrary, but they should kind of correspond to different feature spaces for that word in different ways. Now here they're doing each word is one number. So here they're saying token 8667 corresponds to hello. And initially we did that. We just assigned one number to each word or as a token. Nowadays we assign a whole set of numbers. So we'll talk about that more in a little bit, breaking that down here. So again, that is our embeddings. We take our words in embed them and convert them into numbers or tokens here. And then we have this positional encoding here, this positional encoding here. That allows us to, for every word, kind of denote where it is in the sentence or the string there. And that will allow us to get rid of our recursive connection. So rather than having the network remember we have the word and then and remember its state and then send the next word, we're going to send it each word and then the position of that word in the sentence in some sort of positional encoding. And we'll talk about this. One way of thinking of this is kind of like, have you ever had to remember a sequence of items for like biology class or the planets or something like that? And what's one way of doing that? You might put it to a song or a melody or something like that and kind of sing it there. And that's what this is kind of doing, is it's taking our sentence, our words, and putting it into kind of a way where we like almost putting it in the song. So if you remember each tone, you'll remember where that, what helps you remember where that is in the sentence. And again, we'll get more into that later on today. Okay, so here's our idea. We specify words, hello world here. We send it to the encoder, we detect our features, and again, we're getting out French out at the end. Now, to get the actual French out at the end, we actually have to do some what we call softmax and some just normal neural network layers out at the end here. So we have this. We also have a special key that we feed in here. So again, we will specify some words here and have it generate rather than having it generate the whole sentence, we'll have it generate one word. What's the first word? So if I give it this sentence, here's the first word it's going to have. Now, once we have that, we're going to feed in to the decoder not only the feature space, but also the words we've generated so far in the sentence. So we do kind of this recurrent stuff, but it's a different kind of recurrent. It is just the past, what we've generated in the past here. And then we use a special token for the start of the sentence. Here it's denoted by SOS. So we started the sentence and then we did bonjour here, and then we're generating the next item in this word. And then again, now we're feeding the next couple words plus the whole English sentence into our transformer and having it predict what the next word, and again, eventually it'll predict the end of sentence word for this. So again, this kind of tries to do this mapping of how this works. Okay, I'm going to, okay. We'll talk about one more thing here, and that's what's in our encoder block. We're going to use attention here, and we'll see a little bit more about attention today. But attention is just a way of mapping, what parts of the sentence are important. One thing that's interesting with transformers is we switched from attention where we were, let's see if I can go. Earlier attention was looking at the output words and the input words and trying to figure out what output words were important or what input words were important to the output words here. So in order to generate this word, which of these words were most important or helped to generate that word? So the attention went from the input to the output sort of stuff. Now we're going to use something called self-attention, where we're just going to look at the input and see how important are different words to the other words of that sentence. So how much do you need to know one word in order to or understand another word in the sentence? So that's called self-attention here. So we have a self-attention mechanism, and we're going to have actually multiple, like we stack one. We're going to have when you're reading a sentence, you might want to pay attention to multiple things, like this pronoun is related to this part. You might also have to remember what gender the sentence is in. A lot of language changes the wording or the structure of the sentence based on the gender of the sentence there. You might want to pay attention to, is it a question or not? So there's a bunch of things you can attend to. So we create multiple copies of this attention thing. So that's why it's showing it up and breaking it into parts. So there's actually multiple attention paths that this one thing represents. And then that goes into just a traditional feed-forward network. Remember when we started neural networks weeks ago, we had feed-forward layers. So we're still using those in different spots in here. So, okay. Okay, let's mention this too. Now, one other thing we have from convolutional neural networks is this idea of a residue connection, where when we're stacking all these things up, we're going to jump over some of the connections or some of the ideas here. So we also often add these residue connections in here to do this. So, okay, I'm going to go back here and jump into the actual paper. So this is the actual paper. You can actually read this original 2017 paper. Because this is such a key thing. Google has put copyright notices that gives everyone permission to reproduce this in scholarly and journalistic work here. And again, this is actually a collaboration between people at Google and the University of Toronto who are working together. And again, you can read this paper. It's not that bad, but it's a technical paper, so it gets a little hard. But again, this is the diagram that we'll see again and again here. And again, Google has largely released this without copyright, and we'll see this. So again, we'll see and work through this paper a lot, where we have inputs, we have input embeddings, we have positional encodings. We're feeding it into N of these encoders. Each encoder has a multi-head attention here. We have a residue connection over here, some normalization here. We have a feed forward network, another residue connection here. And again, we're feeding, these are stacked n times. And then that creates some sort of feature space, and that stuff is mapped over here. We also are taking the output that the network has created so far, the words it has predicted so far, embedding and positioning and coding on them, feeding those to multi-headed attentions and normalizations. And again, then we're taking this feature space here and then a feed forward network and some more normalization. Again, this is the decoder, and we're duplicating the decoder multiple times. And then finally, we have just a normal linear feed forward layer and a softmax feature layer to predict the probabilities. Again, it talks about the encoders. Their encoders, the N was 6. They use 6 identical layers here. Talk about the size. They talk about the decoders. They had 6 decoders there. They talked about their attention and their multiple multi-layered self-attention here and how they set that up for this. And then this attention we'll see deals with these blocks, these little matrices that are generally called Q, K, and V for query, the key, and the value. It's kind of a lookup sort of idea for this. We'll see, we might see that a little bit more. And again, this is a single attention layer, and they're putting this into multiple attention layers and doing multiple layers of this in this multi-headed attention here. And again, they're talking about some of their calculations and how they produce some of this stuff. They talk about their embeddings and how they're generating the network. They tried different layers. They tried recurrent networks, convolutional networks, self-attention, and they look at some of the ideas here. They talk about how they do positional encoding. They do a lot. This is very complex, and they managed to bring it down to just this. These simple equations. Well, I don't know if they're simple equations, but these equations. So we'll see if we can explain what these equations mean later on. But again, basically, they're trying to use wavelength geometric progressions to encode these. And again, you can almost think of those as notes. We're going to encode this stuff with different wavelengths, different tones, multiple different tones are going to encode this stuff. So they talk about why are we using self-attention, their training, how they did the training, and then they compared their model with other models here. It doesn't seem like it's that exciting. I mean, it really builds on a lot of stuff here, but this really performed really well for this. So let's look. So we're going to look at 2 companies that do have some good background on transformers. One is IBM here. This is the IBM article on transformers. Maybe. Let that be. Okay. So the IBM's resource on transformers are kind of long. So I've tried to kind of quote certain parts of it here that I think are key. So what are the main parts? The 2, IBM says the 2 primary innovations of the transformer models. So these are the 2 new things. One is positional encoding. So instead of looking at each word in order, it appears as a sentence. A unique number was assigned to each word there, and its position was encoded in its tokens there. So the sequence of the words is encoded in this positional encoding. So again, it doesn't tell you much. We'll try to look at this more later, but positional encoding was important there. And the other thing was self-attention. Rather than having attention to the output attending to the input, here we're taking the input and attending to the other words in the inputs and understanding that. The other important features Again, how we input, did the embeddings for this, how we converted words into numbers or input sequences. So positional encodings, we mentioned above, multi-headed attention. So we can capture different relationships between the tokens that we want to focus on. We'd learned by this point that layer normalization and residue connections help with convolutional neural networks. They brought those over here. They have the traditional feed forward net layers. All the layers are stacked together. They have a special output layer. Their training is typical. They use something called Atom. This is the same sort. We use Atom when we've been training convolutional neural networks. So the way we train things with back propagation, changing weights. So again, we'd give it some input, see what the output that was predicted was. Then we would see if it matched the output we thought it should have. And if not, we would go through and change the weights through the whole model, tweak the weights a little bit so it's a little closer to the predicted result. And we do that again. So here's the IBM article walking through this, talking about what's new here, the two big innovations and all of these different features for this. The other area I want to look at is NVIDIA here. Are you familiar with NVIDIA as a company? Have you heard of NVIDIA? What have you heard of them? What do you know about NVIDIA? What do they do? Gaming stuff. Gaming hardware? Yeah. Or they put chips, yes. They make like graphics cards and stuff like that from chips. I'm not 100% sure they actually make their own chips. They might. But they get these complicated chips, put them together and make graphics cards and stuff like that. So if you're a gamer and you want to game fast, you'll have you'll buy an NVIDIA GPU to put in your device there. Anyone bought NVIDIA stock recently? I'm historically really bad at investing in tech companies. You would think I'd be better. I remember 20 years ago when this new company called Google came out, and my mother and some friends were asking, should we buy Google stock? I don't buy Google stock. I mean, it's just some guys in their garage. They wrote a web spider that crawls the internet and creates a little database and you can search it. I mean, anyone, I could grab a couple friends and we could do that in a weekend if we needed to. There's nothing special about that there. So I did not succeed there. I remember when my mother she had bought some Apple stock back in the Apple II days or whatever, back on the old days. And then the Macintoshes, I grew up with Macintosh computers, we liked them, but then they really floundered for a long time, for a number of years. And so she's saying, I think we should, she's asking me if I thought we should sell the Apple stock. And I've never been a fan of Apple. I said, they're very segmented, and I don't know, what are they going to do? Make a phone and sell a phone? I mean, so they'll make $10 on a phone or something like that. No one's going, it's just Apple there. So I'm historically awful at tech purchases there. So luckily, my mother knew that and just would not listen to me. Well, she'd ask, but she would not base her financial decisions on that. So this is the NVIDIA here. Again, this is in 2023. Its price was like $14. And then it's gotten up to like $140 in the last few years there. So it has really taken off as far as this. Because again, it has been the heart of this transformer models and a lot of the training, a lot of this stuff. If you're going to train these big models, you need lots of computation and you need lots of GPUs. And in general, NVIDIA GPUs work quite well, are optimized for this sort of stuff. So again, NVIDIA is going to talk about this here and what this does. I'm actually going to jump back here where I've just pulled some stuff out of that larger article here. So what do they say again? And hopefully now we're going to try to understand this. Transformers use positional encoding or encoders to tag data elements coming in and out of the network. So again, there's this positioning encoding. Again, attention units follow these tags, calculating the algebraic map of how each element relates to the others. So the self-attention calculates how does this algebraic calculation or thing, how do the different words or tokens relate to each other in a sentence. So attention queries are typically executed in parallel by calculating matrix of equations called multi-headed attention. This is what NVIDIA does really well. They do matrix multiplication very fast on their chips. That's why what graphics are, a lot of the graphics that we use in games and stuff, a lot that is all just matrix. We've converted all that to matrix multiplication, numbers on the the display and all this stuff and stuff. It's all been converted into this. And again, if we can get this attention stuff to be simply matrix equations, we can run this very fast here. So, the article also talks about self-attention finds meaning, and it talks about some example sentences here. So here's a couple of sentences, and we want to watch the pronoun or the it. She poured water from the pitcher to the cup until it was full. So what is it in this sentence? She poured water from the pitcher to the cup until it was full. And again, this is where attention matters, where we're trying to say, how do these words relate to each other? Poured and water and pitcher and she and cup and full and it and until. How are these all related to each other? So, and it refers to the cup until it was full, it being the cup, because the water is going from the pitcher to the cup in this example. But in this sentence, she poured water from the pitcher to the cup until it was empty. Now it corresponds to the pitcher. It was empty means the pitcher, because the water is going from the pitcher to the cup, empty there. So again, we want to be looking at this idea of attention and how these words and their meanings all map together here. So again, these are two exact similar identical sentences, except one says it was full, and another one says it was empty, and the changes, empty or full, changes the meaning of it. So until you get to this full or empty, you can't determine what it is actually in these sentences. So again, meaning is the result of a relationship between things, and self-attention is a good way of learning those relationships. We look at lots of words or sentences and or phrases and stuff like that, and from them we learn the relationship between words in sentences, what words correspond to what other words in different sentences. And then they're also talking about, machine translation was a good way to validate self-attention. It needs both long and short-term relationships in the words. Yeah. Okay, so we've looked at IBM, we looked at NVIDIA. Let's look at AWS. So AWS is Amazon's cloud service. So this is Amazon. Boy, our network is a little slow today. Okay, that's okay. So I've taken the stuff out of the AWS article and posted it here. So again, here's our picture that we'll see multiple times. We'll see multiple times here. And again, this is the picture from the original paper here of a transformer model for this. So what are the parts of this? So the first thing, our words are going to this input embeddings. This stage converts input sequences into mathematical domain that software understands. Input sequences are broken down into a series of tokens or individual sequence components. For example, the sentence, in this sentence, the tokens are words. And then embeddings transform these into a mathematical vector sequence. And when we say vector, we mean multiple numbers. You can visualize vectors as a series of coordinates in n-dimensional space. How are you visualizing n-dimensional space? So we have coordinates in n-dimensional space here. They give an example. Maybe the X represents the alphanumeric value of the first letter, and Y represents the category here for this. So they talk about banana being represented by 2, 2. B starts early on there, and the first letter and the second letter represents it's a fruit here. Mango would be like 13, 2 for this. So you could represent words in different ways. I mean, that's okay. I don't know if those are great, but again, if you think of different fruits, what are some features of fruits that you'd probably want to encode there? So, maybe one of the dimensions is the color of the fruit. Maybe another thing is the size. Maybe another thing is it edible or not there? So again, those are what we would think of as features there. But the computer is going to learn its own features here. So this is one place where we use pre-trained networks. So Google and other companies early on, like 10 years ago, needed to do some embeddings. And so Google just trained, and a couple other companies just trained a number of neural networks just to generate vector representations of this stuff and try to find good vector representations of things. And what they did is they trained networks to create an internal vector representation. And then based on that internal vector representation, like those 10 numbers, could the network then generate the word again? So can you create an internal representation with just a few numbers and then generate that word again? And once we had that, again, similar to like convolutional neural network, we had chopped it off and threw out the top half of the network and said, okay, now we have a network that we can give it any word and it'll generate an internal representation of 10 numbers. We're just going to use that now in our network as our encoding layers for this. So these are all pre-trained now. You can just grab and, you can go to Hugging Face and grab an embedding layer. And there's a number of standard ones out there. Okay, so that's the embedding layer. Positional encoding here. This is, again, trying to encode the order of the input sequences, the position of the words in the sequence. Is this the first word? Is it the second word? Where is this? Let's see if this is the article I'm thinking of. So what we're doing is that rather than just encoding, so we have a sentence, I am a robot. And rather than just saying this is word 0, word 1, word 2, word 3, we're going to try to apply some more complicated encodings for this. And again, now we are doing, so we're using some of these sine waves here. And you can think of them as numbers, as musical notes rather than sine waves. That's what I do. So each of these is a different musical note. And then we we basically create a chord for each of these sentences. So each of these sentences has a chord. So we have so much of this note and so much of this note. But rather than like chords, you usually are just playing it or not. We are saying we have like a volume switch on every every different note. So we can say we have a little bit, 84% of this chord or note, 54% of this note, and 10% of this note or stuff like that. So we're encoding it that way. So we have our positional encodings here. Here. And now we're getting to these transformer modules, these encoding modules. So in there we have this multi-head self-attention and a feed-forward network. So again, we have a multi-head attention and a feed-forward network. Here we have some residue connections around this and some normalization with that here. There are some links to some articles here. And again, we finally feed that into, so we do all of our encoding, we do all of our decoding, and then we have a linear layer and a softmax layer at the end for this. I think my favorite view of this probably is this illustrated transformer. I put it the very last link in here to look at this. And again, this is kind of try to break it down here, taking an encoder to a decoder, multiple encoders to multiple decoders. And again, we have some input in one language and output in another language. Originally, that's what all this stuff was really developed was for language translation. We really didn't think there was a big market for just generating words for things. But we soon learned that, you know, you could generate a set input and have it generate the output in the same language here just fine. So, and again, each of these encoder things is made up of a self-attention and a feed-forward layer for this. And except same with the decoders. The decoder actually has two different attention modules, a self-attention for the input of its previous words, and then it mixes the encoder with the this stuff into this new attention stuff, and then a feed-forward network. Here we're talking a little bit about the encoding of the words. So again, every word is going to be a vector of numbers here, the embedding algorithm for it. So each of these words is going to be represented by, again, in this case, 4 numbers. In reality, I think we're often using like 32 numbers. Every word is represented by 32, a vector of 32 numbers that were trained. Oh, no, that was wrong. Our vector size is 512. So every word is represented by a vector of 512 different features here. So again, we're feeding in each of these vectors in here. We're generating a vector and we're feeding that on. So we're keeping these words, these long vectors as we go through this. We've talked about this attention and like words like it. The animal didn't cross the street because it. So what was the it? And what does that relate to? And this is trying to show what parts of the sentence it should be attending to help it understand it. So. I'm trying to figure out how much to talk about attention. It is quite complicated. So I'm going to go over it maybe in a very simple way, and that if you're interested in it, you can learn more about it. So again, what we have is we have these embeddings, these words. Each word is a vector. We're showing 4 things, but I can't remember. They're really 512. Oh, here they're saying, yeah. So, and we are looking at a query, a key, and a value for this. And what this is trying to do is there's something called key value lookups in computers where we specify a key and a value. And then we have a query that says, oh, if I have this key, I can generate this value sort of idea. And you can kind of break that down into these matrices for this. So again, for any token, we look at its key value query pair here. And again, we generate a matrix, a two-dimensional array kind of for each one of these stuff. And again, they're showing these very small, these are quite large. So our embeddings, I think, are 512, and our encodings, our attention are 64 bits. So each of these are not 3, but 64 bits wide here. And again, these will be looking at these values. And again, at each word of the past. So this matrix will help us calculate how important each of these symbols or parts of our embeddings are into the whole thing. So this matrix is 4 by 3 here. But again, it's really 512 by 64 is each one of these values. And again, we have that same thing for the queries, the keys, and the values for this. And this tries to walk you through this calculation of how we use this these values given some word and Q, the query, the key, and the value, do some calculation to get some scores, and then we can predict how likely that word is to be like the next word or an important word in here with this. So. Okay, I'm going to leave the rest of the self-attention or this attention out here. So these attention models are these transformer models are really based on recurrent neural networks here. They take a couple things from convolutional neural networks, but they're very much these recurrent long, like, what we've seen from long short-term memory or these feed-forward networks with attention put in there a lot. Now, are they the best way? Right now, they are, but there are competing ones out there. What was 2 weeks ago? When we look at image generation, is that just last week? No, that was when did we do image generate? Where we generating images? 2 weeks ago, right? And remember, how do those image generation stuff work? We did diffusion models. So we started like with random noise, and we learned how to go from random noise to images there. So there are people trying to take that sort of idea and apply it here. So rather than taking, learning this attention stuff and memorizing all this stuff, can we change the network structure so that we actually look at like random noise and start random noise and train a model to, predict better sentences, construct a better response, not one word, not just always predicting the next word, but predicting, kind of generating the whole response all at once there. So when you think, what runs through your brain here? A lot of people have been asking that lately. So do you have a conversation running in your head most of the time? And is it running in English Or is it running, and again, if English is your primary language, or is it running in a different language there? Or is it running in a language? Is it running in a language? And are there times where it's not a commentary in your head, like when you're visualizing like how to drive to the mall from here and the directions? I don't visualize, I don't, my mind doesn't talk me through that. My mind creates a map, a visual map in my head. So again, what are some of these internal representations? And then what kind of models should we be looking at? Should we be just using these word models? Are there other models? And so again, there are thousands of research labs across the world trying out lots of different models and trying to figure out what might be the next best model. So right now, transformers are working really well, but we'll see they have limitations. So again, what is the whole idea of transformers? Basically, they are trained to predict the next word. We take lots of text, we feed them through this model here. So again, we'll take a sentence and feed that into the model here. So we'll take the whole sentence, push it into the model, one word at a time here. And then we'll start it, we will start creating internal representations as it sees more and more words here, and then feed that through, and it eventually will generate an output word. So we'll feed in a bunch of words and it'll generate an output word. Then we'll take that output word, feed that in here, and then again, you know, it has this internal representation here, and then have it generate the next word here. And then we'll again say, okay, here's the last two words you generated. Here's what the input was here. Can you predict that? And so with training, what happens is that when it, like, let's say we're trying to predict the third word, we've predicted two words, we've fed in the first two words here, we've sent some input sentences here, and then we're trying to generate the next word here. And if it gets it wrong, because again, maybe we're learning from actual sentences here. So we have the actual text we're learning from, we have its predicted text, and it predicts something is wrong. We'll then take that and we'll change all the weights throughout this whole network here. Now, some of them we don't change. We don't change the input embeddings that's been pre-trained, and we don't change the positional encoding. So these sorts of layers are fixed, but all these other layers will change all the weights in all these other layers. Now, how many weights are there to change? And again, when you hear these, they'll say it's you know, 8 or 7 million parameter model. That means there's 7 million parameters, weights in this model that can be changed for this. So whenever you hear how many parameters are in the model, think that's how many weights can be changed when we're learning this model for this. So he's predicting the next word here and doing that. I sometimes struggle with, well, we can't really train a transformer from scratch. You know, right now I think they're saying it costs like $1 million to train a new language model. And so it's not a classroom week-long project that we can do here. I can't assign you an assignment. Just train a new language model there. This is not going to work today. We don't have the hardware stuff. So we're going to look at a couple things this week. On Thursday, we'll look at fine-tuning a transformer model. So if you take a transformer model that learned something, can you fine-tune it to be good at something? So if you have a general language model and you really want a language model that's really good at legal documents or doing homework or doing math, how do you fine tune a transformer model? So we'll look at that. And that'll let us do some actual training and work with a pre-trained transformer model. So we'll look at doing that on Thursday. Your home, the project this week, and again, usually with projects, I've been giving you a notebook and work on that. I really couldn't find a good way of solution this. So you are going to do some experiments with large language models, but you are going to try out some commercial large language models and experiment on them here. So for example, large language models have some problems with spatial reasoning. They're trained to predict the next word, but they build in some internal representation so they can do that. They build in some internal representation that kind of takes some things, but they struggle with some things. So here's our sample sentence. Imagine you are in a small room with a desk set against one wall with a chair in front of the desk. There's a bookshelf on the wall opposite the desk. If you are sitting at the desk, can you see what books are on the bookshelf? So we're trying to describe a thing where you're, like Johnny, you're facing that way on a desk, but there's a bookshelf behind you and you can't see the books behind. If I'm sitting here at my desk, I can't see the bookshelf behind me. That's what we're trying to describe. I don't know if this is a great prompt for that, but that's what we're trying. And then hopefully the AI will say, no, you can't, you're facing towards the wall. And so you can't see, and the bookshelf is on the other wall and you can't see that. That's what we're trying to get it to say. So we're going to try out different language models to see how they do that. So we'll try spatial reasoning. We'll try some common sense stuff. We'll try creativity, sentiment analysis, emotional intelligence, and some bias and fairness questions here. So in each of these, I'll give you a sample prompt, but I really want you to come up with your own prompt similar to that. And again, you can use AI to come up with a prompt here to help you with this, but you want to come up with your own prompt. And then you want to compare, and you're going to compare 3 different models out there. Now, since we're doing some experiment here, we have to dive down a little more in detail. So like if I just go to ChatGPT, I don't want to just say ChatGPT because ChatGPT actually has multiple models. I've used changed. So I don't know, and I'm interested to see because I have some access to some models you might not have. But at ChatGPT, this is the model, ChatGPT 4.0, or yeah, here. And if I click, I can switch this to some other models here. So they have O1 for advanced reasoning, O3 mini. I've been using O3 mini high because it's really good at coding. And then there are some more models. There's the old ChatGPT 4 mini and the legacy ChatGPT 4. So I don't know what models you will have, but most of these will have some place on the screen where you can choose the different models. And you might, I don't know if I have a paid subscription to ChatGPT, so I know I can certainly see more models, but you want to do that. Now Gemini, I don't think we can't sign up. We can't do that at our current thing. So if you've got to use a different account for Gemini for it. I use my one of my other Gmail accounts and access Gemini through that there. So if you want to try Gemini, you can do it. And again, they have 2 models that I could see that I can have access to, Flash and 2.0 Flash and 2.0 Flash thinking experiments. There's DeepSeek, and again, there's 2. This is the new Chinese model that's out there. There's Claude. So again, if I go to Claude, I'm going to try Claude out. I'm going to continue with Google. Sign my soul away. It's interesting. So there's a little note saying it. They switched me to Claude Haiku rather than Claude Sonnet. It's temporarily unavailable for the free plans because of demand there. So usually you can switch. So like here, how can Claude help? You can down here, you can choose the model. And as a free user, I can usually choose either one of these. But again, right now, because it's the middle of the day, Sonnet seems like it's too busy. And I don't have a paid model. Now, there's also some older models, and sometimes it's fun to try out these older models especially when you're trying to get things to fail. So try Claude 3 Opus. You could try that and see how that works with some of these. Why didn't that actually change? Okay. Okay. They're having some problems. Claude is. That's okay. So again, your job is to pick for this project is to pick 3 models. So you could actually do 3 models from one vendor if you wanted, or you could do 3 models from different vendors here for this. So pick 3 different models, and then for each one, you'll create a prompt to test out this, and then you'll analyze the results. I don't ask you to paste all the results in here. I suggest you might want to have a separate document where you paste all the results in there. If you want to put all the, I assume you make a copy of it. If you want to just have the results in here, you're welcome to just do that. For that, that's fine. But I didn't require it. If I were doing it, that's what I would do. I would just stick in a table in each of these things, and I'd post in the 3 results here, but I don't know how you want to do that. I just want the fact. You might just have them open in multiple tabs and analyze it from there. That's fine. So again, that'll be your job for the project this week, is to analyze these models as far as spatial reasoning, creativity, their sentiment, emotional intelligence, how well does it display these sorts of ideas? Okay. So that's the project. The discussion this week is somewhat open. So again, I'm still interested in AI news. If there's news out there on new things with AI, certainly put that in the discussion. The other thing I thought would be interesting is to see, I don't know if you know what a podcast is or if you listen to podcasts, but podcasts are these audio commentaries out there. And if you don't listen to podcasts, you really should listen to some podcasts, right? You should be finding some podcasts to listen to out there. So there are, there's thousands of podcasts, but maybe you don't have any AI podcasts in your stream. So here's a couple common, well-known AI podcasts that you can do here and listen to for this. Where did I'd updated this? Every once in a while, I update things, and for some reason, I must not hit the save button or whatever. But I added. I'll have to add that. I want to add Perplexities podcast to the list. Discover Daily, because they're not always AI focused, but a lot of them are AI focused with this. And it's all, the whole podcast is computer generated, which I find interesting. They use AI to look through the news, figure out the topics, and then to generate the 2 voices of the people talking. So the whole thing is AI generated. Let's see if I can.
Infrastructure providers, multinational corporations, where operational disruptions carry maximum financial and societal impact.
It has a little bit of that podcast or that AI generated podcast feel to it, but I still find it interesting because it's all AI generated. So I'll add that to the list too. And if you know of any AI podcasts or stuff, again, and then if you don't do podcasts, if there's someone on social media you follow or something like that, feel free to, do that. You don't have to do a podcast. You can do, again, AI news. And I said AI in the news, it doesn't have to be in the newspaper here, I'm talking anywhere on social media or something like that that you find an interesting thing. So. Okay, so that's what we're doing. We're doing Transformers this week. Why don't you spend some time now going over an explore activity? You can watch any of these. And again, under the learning resources, that first video is just a 10-minute video. I really suggest you watch that one there. So any question? I'm going to wrap up, I think, here for the day. Let you go through and decide which explore activities you want to do now. Sound good? All right.